We use the chicken out. Use the chicken.
All right, we're going to get started. I don't know where all the rest of you are gone. There's no event today, I don't know, but we're going to start. We're going to finish off a little bit of serial interfaces today, and then we're going to go on to analog signals, which is kind of like the last big chunk of the class, and the kind of the same stuff as last time. Oh, that was yesterday or 2 days ago. But team registration is due today. This is important. So one registration form per team. If you did multiple, I don't care. I'll figure it out. But that's going to let me make those folders for you. You'll get like a team registration folder or team folder, as we saw in the project overview. And then after that, I'll release sometime tonight. I'll release the schedule of the meeting sign-up sheet. So you're supposed to go to it, fill your name in, and that's when you're going to come and talk to us. We won't have an official class on Wednesday next week. So you don't have to come to class. You may happen to have a time where you're meeting with us during class time. That will be one of the times. Any questions? There's no class on Monday. No class on Wednesdays. Sounds like the best class already. Yes, you know. Okay.
Because you just said.
Any questions? Nope. Yeah.
During other classes?
They're definitely, I'm trying to get probably 22 teams to have a 30-minute meeting each with me, Matt, and James. So definitely not going to be able to get that in the hour-and-a-half class that we have scheduled. So this is going to be a free-for-all. You guys are going to look for, find times, fight over the times. It's going to be great. We're going to try to make them widely available. And typically, we have enough for everybody. Yes?
Is it only on that Wednesday, or is it like the whole rest?
Wednesday, Thursday, and Friday. And if we have to, it's going to be Saturday. Please don't make it Saturday. We'll do that one over Zoom. Yeah.
Do we have to submit our actual proposal on like Gradescope or Canvas or something?
No, you put it in your project folders.
Okay. Are you checking that on Wednesday only, or just like before when we schedule?
Before, this is really, the project proposals is really for you to think, force you to think through the thing. So we're going to go through your project proposal and your slides in the meeting. So it should be there the night before. Yeah.
I don't know if I missed this, but did you say when the sign up for those people?
Yeah, it will go out tonight. Tonight. Yeah, I'll put a post on the outside.
Okay.
Yeah. Okay. Great. So let's finish up serial stuff. Let's see, we'll go back here. And we have a little worksheet problem, but I'll give you the quick review. I kind of did this review last time, but you forgot everything from last time. Totally fine. So for UARTs, how you guys doing? Everybody all right? Fantastic. UARTs, remember, it's one device to one device. It has no arbitration protocol. It could, if you could stick another device here, it would have no way of selecting between the two devices. So from an arbitration point of view, from a topology point of view, it's one device to another device. That's a unique characteristic. There is no clock. It's asynchronous, so the clock has to be recovered. Another unique scenario for this particular chip communication. Other than that, you have to a priori, with all of them, you have to figure out what your data rate is more or less beforehand. But this one specifically, because there's no clock, you have to tell each device what the data rate is beforehand. Yes?
This also seems like a start signal, like the serial.
Yep. Yep. You can look through these things. There's a special start sequence. Then we talked about SPI, so serial peripheral interface. This is the de facto standard. This is the one that everybody uses, but there's no official standard for it. So that has a variety of different implementations and speeds that you have to check through. This one is denoted that there is from the controller's point of view, there's a serial data out, there's a serial data in, there's a clock line. So it's a synchronous protocol and everybody shares the data buses. You can transmit and receive at the same time. That's totally fine. The way you do arbitration is there's a chip select. So there has to be extra pins to check to select which device you're talking to. The controller pulls the thing low to initiate, and the controller generates the clock. It should have made this clear before that clock is only sent when data is being sent. Clock is not continuously going. It would be a waste of power. And basically, it's built on a bunch of shift registers. Packet sizes are Typically 8, sometimes 4, I suppose, or 16, but typically it's 8. And then the other one we looked at was I2C, or I squared C. And this was trying to solve a different class of problems. They were trying to say, what's the minimum possible number of wires we could have to allow one controller or multiple controllers to talk to n peripherals? And so here, there is no control lines explicit. All that arbitration that's hiding who talks is done through an address. So each one of these has to have its own unique address. There's a serial data line. It's not serial out or serial in. It is the same line used by both either peripherals or the controllers to talk. So you have to look here to see, I mean, if you're looking here, you might be seeing the traffic from the controller or the peripheral, and you don't know if you're just looking at an oscilloscope trace. It's 7, 16, or 10 bits. Open collector output. So the reason they did that, this is just a MOSFET inside. It pulls this line down for a 0. It lets the line go back up for a logical 1. This is done so that this device can't put a 1 out, and this puts a 0 out by accident, and you short out the chip. This allows a level of robustness because multiple people could be using by accident the SDA line. Only the controller sends out the clock. Yeah.
Resistor over there, a pull-up resistor then?
That's what we call it. We're going to call it a pull-up because it's connected to the VDD. So if there's nothing connected to this thing, all the gates are open. It's going to pull that line from ground all the way up. And then you can have a pull-down resistor, which is going to pull the line down. The weird one about this protocol is that well, addresses for each one, yes, but devices, speed of the bus is dependent by hardware choices. That's weird. Normally, you just send the clock faster. Normally, you want SPI to go faster, you just have your STM send out a faster clock signal. Here, you could do that within a range with this, but ultimately, you're going to get to a point where you're going faster than those pull-up resistors can pull back up. You should think back to the for the follow-stat examples we showed with the capacitors and how you had this long charge-up cycle. And so that's an example where now you have to go and change your resistor value in order to get faster speed. All right, so, hey, what's happening here? All right. So, okay. Now, here's your example, here's your thing. I want you to consider, how would you make a one-wire interface? So you only get one wire for everything, okay? And ground, you get a return wire. But you talked about SPI was 4 wires plus a select, or 3 wires plus a select line. And then we talked about I squared C, which is 2 wires. I want you to design a one-wire interface. And the goal is to think through all the things that we just talked about, all those other serial peripherals, protocols, and figure out how to make one that only uses one wire. Got 2 there? Perfect. Okay, send them back to this guy. Gentlemen.
One wire plus
Right. One.
more.
2 more.
I'll do one wire.
Chair over here.
Should be there. Yeah.
That's a good idea.
Dr. Sam, does this have to be a multi-master, multi-slave?
One wire.
One.
It depends on the
Let's say at least multiple peripherals.
No, it's.
But you can eat, once you figure that part out, then you got multi-master if you want.
Like, it's, the voltage in one wire is X, and the other wire is negative X.
So for
transfer.
topology for this new one you're inventing, it should at least be one controller to multiple, but once you figure that out, then it can be end to end.
You have this and then a different thing. So just, I don't know why they do it though. I feel like it's just important.
Okay. See, inside of my device,
I think it's the request data.
Just one wire. How will we do it?
great question.
All right, so how are you going to do data?
On the wire.
Okay.
That's what I'm best at. I call them that.
Just a bunch of boxes.
Yeah, more wires.
No, you only get one wire between the devices. That's one wire. They're called wired.
Other protocol we talked about.
Two boxes with the line back.
You only need one wire.
Can we just have this? Oh, we're designing a new design.
About one.
Use serial packet header.
All that data in clock with one wire.
I did points. I said 9. Remember that it was serial.
Sync.
Separate.
Phase 1, phase 2.
All I compare and think we do a lot of the ICs right now.
I can be up on that.
Wrong signal goes to
Oh, it's UR. What is not even this? Yeah. Because these other two, because 2 out of the other 3 have the with one wire with no clock.
So we want,
You know, so it wouldn't make sense. Wire one would somehow be better than wire.
Wait, what? You don't even have a clock in this draw. You can handle the clock signal, right? So now we can already start describing some of that protocol.
think of algorithms.
I don't know how it works. I just know
Transmitter to receiver.
What are we doing? I'm going to copy down CAN. Yeah, it's 1 bit. No, the other signal is just the opposite of the first signal, so transmit waves. It's not kind of USB. There's two wires, but the other wire just.
That's kind of how it works. Make sure you fill out all these things.
Yeah, one wire, anything is gonna transmit radio waves.
Technically, it's multi-bus because USB.
You're gonna transmit radio waves.
Yeah.
No.
I don't understand what it means.
Look at that and choose.
Like, yeah, I think the idea
Choose
is
the
that you
characteristics that you would
Yeah,
want
you
to
have
make up
like a
this
high-end
mythical
low-wire, like
serial
one of
bus that asks you literally these are your two.
If you're trying to have a here's 150.
Not radio.
Radio waves, so I don't care.
Make us do the physics.
Just let it be.
Like just say that you're driving a
You want one bus. Yeah.
Oh, it can't be a single. It can't be UR. It can't be UR.
You can't do any of those because those two clocks have noise problems.
Don't manually set
You made UR. How something like CAN works, because I think it's asking the same thing.
Maybe from the beginning and just send them.
I don't actually know. I thought CAN had more control lines.
UR has 2 wires.
It's not kind of USB. The other one is the exact opposite signal, so it doesn't transfer.
USB has 5 wires.
So that's USB 3.
You made a worse wire. Yeah, I did.
I'm trying to understand the existing protocol, so I can design one that's maybe similar.
This is why the Chinese were just.
I don't know.
Not when
It's turn. Yeah. How to do this one? I don't want
we signal start.
Power over Ethernet.
The only reason they have a differential bus is because
logical high, like 10 volts, and logical low, be like 5 volts, which is definitely like stupid, but it would probably send.
No, you were thinking that.
John said it actually.
I was.
You could just have one voltage, but maybe think about the circuit. What would the circuit be that captures that?
next for the project.
Oh, you're doing a proposal.
You would get the power.
Doc, the numbers like add to it. I don't know if it's a me.
Yeah, I mean,
We probably should.
what are you guys doing before this class?
There's no class on Monday, so we could just
Draw anything.
Oh,
I draw something. Just tell me how to do it. No, it says draw. Oh, then here.
Is this right?
That's why we have no class.
Also have no class Wednesday. We can at least talk on.
Yeah, I have an exam
Oh,
on
you do?
Wednesday. No, we can. I mean, it's.
This is kind of one way.
Yeah, I don't know. I guess maybe meeting up might be a little hard. We could just do it now.
I mean,
I don't know. I agree. I don't know.
For a power,
we need to submit it.
we're gonna talk to you. It's a power block for you to do your.
So charge up the installation and you connect it. Could be like the start condition.
Well,
Like, hey,
Like 100 cycles. Need another one.
Try and draw out what you think the internal circuitry and logic should be
Dude, that's
from this level point of view.
what did you do?
we were looking at the accelerometer. When we were doing it. That's a good one. We were looking at the wrong fucking thing.
Sure, what do you got? Like that, okay.
Like my partner, John.
Oh, your partner, John?
So you know what? No.
I have no idea. I have no idea.
You send some pulses, and the other side.
I feel like the way you would do it is just have like some type of synchronizer.
Yeah.
Some of them have no arbitration method, that's lame, we're not doing that. Some of them have a little wire.
One synchronizer.
Some of them have, like, the device has an identification.
If you're doing a single wire, can't you still do an identification, like a packet header?
Put it in parallel.
Yeah, to encode.
Okay, yeah.
So what does that mean all the peripherals have?
They all have shift.
They all have IDs.
A little more than
One is the exact opposite of the other one.
Device doesn't really matter.
Yes, but not
How in the world does UART work? That's a great question. It does not.
It's standard. It's
You can send UART with one wire. The other wire is not a clock. So think of the example we gave you.
Only have one wire.
Okay, you send 3 pulses, yes, and then you send no bits according to your clock, and the other side should get it.
Yeah, that's kind of your like
Yeah.
bring it to so like you
Yeah.
know, so you hold it low until
High low, low low, and then you send the end of package pattern. You make it up, and the other side look for that pattern. Realize when the package. That's how you guys work.
It's a battery. Resist. The battery is really high voltage, and the resistor just gives out.
you see the bonus question thing. Design a method for sending power from peripheral to
Is there like a wire that goes through? Is there like a cable that goes through?
volts, and then your high was like 5 volts. So that it would constantly.
No, the voltage is standardized. I think you have to standardize the voltage at least. Otherwise, you're cooking the other side.
Well, I'm saying for this, I think, because I think can does probably I don't think it's 0 volts. I think it's like 3.3 volts or something like that.
We don't have those.
What do you got?
See what
you got.
You could get
Maybe. Maybe. All right. How will we do this? How in the world could you have a protocol that only has one wire? Anybody have a guess?
I think the grounds.
Yeah, so you have 2 wires, fine. You have a wire for ground. Shh. All the other ones lied to you and said that they were like 2 wires or 3 wires plus, but they always had a secret ground. I'm also lying to you. Okay. So just 1 wire plus ground? How are we going to do it? How will we do, well, we already know how many wires. What's the timing methodology? How will we know when to clock in the bits? It'll be asynchronous. Remember, UART has no clock. The receiver has to oversample to figure out where the bits are. It has to sample faster and then guess to be right in the middle of those bits. Okay? How about arbitration? How will we talk to multiple devices? Yeah.
You only have one wire.
Yes, I know. It's amazing. How will we talk to multiple devices? Okay, so how in the world does I squared C talk to multiple devices? Assume we could get rid of that clock somehow. How does I squared C arbitrate to multiple devices?
The address of the device you want to talk to.
Yeah, so now we're going to use addresses, packet headers to talk to them, okay? And topology, if we made up this mythical one, this mythical thing, how many can we talk? Is it 1 to 1? Is it 1 to n or n to n? Could be also, I'm telling you, it could be n to n. There's no reason why not. N to n, fantastic. And we'll talk about complexity in a second. So here's how, this is a literal topology that exists. You can buy chips that do this. I actually made up the example and then figured out it existed. That was interesting. So here's the controller. You have a controller. You have, this is just what the input of I squared C is, or the input output stage of the I squared C. So you have a transistor that pulls the line low, right? It have a pull-up resistor to let it go high. So that's how we're sending data. Then you can send packet headers for arbitration. And you're going to do it asynchronously, which means the receiver, this device, is going to have to oversample the signal to recover the clock timing. And yeah, so you can see that here. There's an interface controller, and then the device has a 64-bit ID. Okay? Does that make sense how it's possible? I'll show you a false data in a second. Does anybody have any questions so far? Yeah. How fast, compared to the other ones, that's a good point, compared to the other ones, what is the general speed you expect this to be? Well, is it as fast as you are? Faster or slower than you are? Faster or slower than I squared, or SPI? I'm going to say much slower than SPI. Faster or slower or the same as I squared C? It's the same physical layer as I squared C, so it's better be on the order of I squared C. Yeah?
Can you cover how it supplies power again?
Ooh, that's the secret. All right, so imagine, I showed you guys, I think in day one, this RFID thing. Basically, it's gonna, you put a 1 out on this wire for a while, then you have a diode, right? That diode's just gonna go and drop that into a power reserve thing, a capacitor. And then when you have data zeros going through, it just has to have enough power on here to survive until it comes back up to 1. So the signal itself is throwing out the data that you need. Or sorry, throwing out the power that you need. So I can show an example. So here, this is the thing running. This is just the same circuit from I squared C. The only thing here is I added in a voltage harvester. And here's the load. This voltage harvester should be 1. What's going on here? What's this value? What? Oh, because I'm pushing out a low on this one. Okay, a low here and a high here. So this thing gets pulled back up to high, relation speed. So this line should be a high. Why are you not a high? No, you're a low. There we go. All right. So now we're going to charge this thing up. In fact, this capacitor is turned green. This means high voltage. So now the capacitor is at high voltage. And I'm going to go send over a 1 really quick, or 0. So we're going to transition to 0 to 1. And we can see that the voltage didn't really drop that much. Here it's actually, I think it's the red line. So the voltage was able to stay high during that little blip because the capacitor stored enough charge on it. And then we can send data back the other way. So here we have the target went and sent data back. So now we have the same physical layer as I squared C, except now we also have to take control of timing. You have to do the asynchronous clock recovery. Nobody's excited. That's exciting.
Does it necessarily have the registers high on both of them where you can read or write anything back and forth?
Well, just the same as with I squared C, right? The default state is these buses are left high. That's actually how this thing charges up. And then you would have a start condition where it's pulled low, and then you send out your bits. Yeah?
When you have your controller pulled down,
Yeah.
pull it low, why does the capacitor not like discharge?
Because it's large. It's just, It's not, you can't, we're not instantly pulling, like, put this load on here. So let's just say the load is, I put a 10K on here, which just say that's the power consumed by the peripheral, which is reasonable. And so let's see, is that what this signal is? Where is it? I don't know where. I can plot it. V-harvest. V-harvest is there. Okay, so that's that blue signal. And then if I send data out, the red line went down a little bit, right? But it didn't brown all the way out. And so you just make the timing of your bit small enough so that you don't brown out during that period of time. Yeah?
You want to send a lot of zeros.
Then you should design your protocol such that you cannot, and design your protocol, say you have 8 zeros that you'd want to send out. Then you'd want to make sure that you spec your capacitor large enough such that 8 zeros can make it through. Yeah?
Do you need to have the same amount of ones as zeros, or is charging faster than discharging?
Charging, no, I guess they're about the same rate, but there's going to be a lot of time between packets, right?
Yeah.
So that's the charge time. So like RFID tags don't have any batteries in them, and they have little capacitors. And so what happens is when you take your phone, your M card, you charge it up essentially, and then it sends out ones and zeros, RF energy or no RF energy, and it's able to survive long enough to do the entire protocol and send back the data. So this, I'm telling you by proof of existence, this is possible. Yeah?
I guess the amount of charged is enough to support the amount of ones that the target wants to send? Or is the capacitor's voltage itself just the powering like every single like logic thing? Like what's the capacitor like storing, and why do you need the storage?
Why do I need a capacitor? So this 10K represents all the digital logic on that peripheral. So say you have a little temperature sensor, and it's on your I square, what is this, not I square, this is one wire, right? Then this capacitor needs to hold all the charge required to power that thing while there's a 1, or while there's a 0 being sent. And so now you have to design your protocol such that you know you have upper bounds on how many 1s could possibly go out, so that you can't discharge yourself by accident. And getting a 10 microfarad cap is literally 0.001 cent, right? It's a little device little piece of speck of rice that you basically put on your PCB. It's very small, very cheap. Yeah.
Does it cost charge to send a 1 from the target?
Oh no, it doesn't cost charge because that comes from here,
Right.
We don't actually drive a 1 on this one. We only drive zeros. Yeah.
Would there like be a way where you could set your like high voltage to be different and your low voltage to be like higher than 0, so like 3.3 and 5 or something like that, so that you're always getting charged? Or
you could, it just makes things complicated, and then it may not be worth the trade-off. So say, it's interesting, I'll repeat the statement. What happens instead of having the 2 logic levels be, say, 5 volts and 0 volts, you made the lower logic level like 0.3 volts or something? Well, that is below, that particular voltage happens to be unique in the sense that's a diode threshold, but then you'd have to be able to use 0.3 volts. And that's kind of hard. You would want to have a buck converter or boost converter to kick it up. But maybe you did something slightly different, which was the difference between 5 volts and like 5.5 volts, and then you guaranteed you have enough voltage for logic. You could do that. I just think that what the trade-off is like, this isn't that hard to do actually. Like, there's billions of devices on the planet that kind of work this way. All the RFID tags, like, it's not going to be hard. So you just put a nice big capacitor, 10 microfarads, and you'll be fine. Yeah.
I know with when it comes to the asynchronous, use the oversampling or
correct.
Like, where would that be in this?
So that is here, past this stage. You're going to have a little ring oscillator that's going to be kicking around. You already know, you look through the data sheet to figure out what the baud rate of this thing is. This thing's sending data out at the right rate, and then this thing is oversampling to make the decision of where in the circuit it should, where in the bit stream it should sample. Does it make sense? So I realize it could have been a clever professor and tricked you all and been giving you an impossible problem. But now that we've explained it, does it make more sense? Or you're like, this is still impossible? I got Yeah,
Synchronization like work.
just like UART. Do you want me to go back over UART? All right, let's do UART for a second. My goal is literally to teach you things. I will teach you things. All right. So remember, the challenge with UART is that you're just getting edges. You don't know when the edges are coming. You need some way to know when to sample in between this data. And this thing is supposed to slide back and forth, but I still haven't fixed it. So the problem is you're pushing a kid on the swing, and when do you push? If you don't know, you might be out of phase, so they call it phase misalignment. If you push while the kid's all the way out there, you make no progress. You have to push just when. So how do you figure out when you should push? You need some way to look at the signal to figure that out. Well, they give you a mechanisms for that. They say when you go from high to low, when you make a transition, this is not data yet, this is just a start bit. So when you see the transition from high to low, then what you do is you count whatever you're set up to. Say you're doing 16 times oversampling. What you're going to do is you're going to go in, first do 8 so that you're aligned in the middle of the bit, and then you're going to do 16. So now you're aligned in the middle of bit 0. Okay? So this oversampling clock, so even if you're off by a clock period, right, that's okay, because you're over 16. So if I'm plus a clock period or minus a clock period, you're fine because you're still within this window. Does that make sense how we're doing it? Yeah.
Is the baud rate referring to how much we're over?
No, baud rate is the symbol rate of how symbols are going back and forth. That's the agreement on the size of these bits.
But like, what if one person's clock is slightly off? Like, doesn't it shift? Like,
yeah. So what happens if you're supposed to be something and the other person can't quite get to it? And that's very common, that you're hertz off or tens of hertz off on that signal. The question is, how long until an error occurs? Well, these packets are only 7, 8, or 9 bits long, plus start bit, a parity bit, and a stop bit, maybe 2 stop bits, depending on your protocol. So that accumulated error has to be so the error between the two signals has to be within this time span. That's the requirement. But 8 bits isn't that long. And they actually have tables which you can go look at that will show you, here's what your expected error rate is going to be from this amount of mismatch.
There's a start bit at the start of every single packet.
Yes, every single packet you are reacquisitioning the clock rate and redefining when you're supposed to be sampling. Yeah.
How does the system know how many clock cycles there are like within one cycle of the baud rate?
Because you told it. Because you were going to say, here's the baud rate. And then the manufacturer said, STM says, well, we're just going to oversample by 16 times, or maybe 8, or maybe 32 times. Whatever the hardware people who made your peripheral does, that's what they're going to oversample at.
Okay, but like even with oversampling, the baud rate can be modified, and the clock cycle is the hardware time. How do we make so how do we deal with the error?
Okay, so let's go back to here. You're saying that this clock could still be off, right? It could be slightly off because you have a clock divider with a prescaler, and that's all being sent. You're taking from remember that clock diagram we showed that was super confusing back when you started timers? You're going to send that clock through your STM32 in-cube ID and send it right to your UART module. And so then you're going to try and get it to be the right clock speed, but it's not going to be perfect. And so there could be errors. You're going to accumulate errors over time. The trick is it's unlikely you're going to accumulate so much error that you miss a single packet, that you miss these last little bits. That would be too much error. And because for every single packet that comes in, you figure out, you look at the start bit and then retime the entire sequence, it doesn't matter.
So like number of clock cycles per baud period is dynamically calculated when you set the baud rate.
Yeah.
Sorry.
No, that's fine.
could you go to the next page? So like maybe this is when we latch the data.
What's this?
The like, you know, yeah, this is when we latch.
Yes. Yep. Now you, as programmers, don't have to do anything. You just rely on those very, clever hardware engineers to actually do this for you. Your peripheral has all this built in. You don't have to oversample anything. You just have to know it exists and why it exists, how it works. Yeah?
And the peripheral has its own internal clock.
No, the peripheral is driven by a clock that you select. So remember, it's one of the 3 clock sources. It's going to be their external low frequency oscillator, external high frequency oscillator, or ring oscillator internally. Then you're going to take that clock signal. So in your case, on your STMs, it's 120 megahertz. And you're going to use dividers and prescalers to prescale it down to be 16 times the baud rate that's coming in. Now, thankfully, CubeIDE, so magical, WYSIWYGs all that away from you. It just works.
But the main idea is once you know how quickly to oversample, you go halfway from the start signal and then kind of start doing it.
Yep, then you do your 16, yeah. So all this clock generation is figured out for you because that's just how the peripheral is set up. Internally, you tell it basically what's the baud rate. You put that effectively into a register, and then it will figure out, it will just oversample by 16 or 32, whatever the oversample rate is for that particular baud rate you put in there. You don't have to do anything. Yeah.
And this clock is internal to the UART?
Nope.
No. But we're not sending the clock, so
Yes.
how do we know?
You are sending, the clock comes from your main clock tree.
Right.
This gigantic mess of fun. Oh, look, there's your UART right here. It's on here. I even knew it. I knew it. So here you would go and select your clock tree and you go through a bunch of muxes and look at this prescaler. This is your advanced peripheral bus prescaler. And now you have an advanced peripheral, it's a high performance bus, advanced peripheral bus prescaler. And then you're going to send some version of that to your UART. And I bet your UART itself actually has a prescaler in it.
But how are you sending it? So there is a wire that's connecting the clock to the UART.
Somehow we could trace this rat's nest, yes.
But there's a wire that's...
Yeah.
Okay.
Yeah.
It's just not sent with the package, it's sent separately. Isn't the whole thing about UART that it's asynchronous, you have to figure out your own clock?
Yes, so we're talking about on chip. We have a peripheral that's a UART timer, the UART peripheral. You're going to use your APB to send data to it. Part of this clocking tree structure also sends a clock signal to control that peripheral. So you could use P clock, let's just say it's P clock. You could use a different clock as well, but then it's going to have its own scaler inside of that to take that clock signal and turn it into the correct timing necessary to generate packets with the correct size, or the correct baud rate. I bet you think about it, come and talk to me. All right, we're going back like 3 lectures. It's exciting. Like all the logical errors I clearly have made and failed to teach you. Fantastic. What other questions do you have? Yeah.
We have like this additional clock as far as like connected to like a flip flop such that it's activating at this increased rate, reading in the value that's there, determine whether it's like a 1 or a 0. Like you know when to sample like.
And are you talking about the peripheral or are you talking about the STM32?
For, I guess, determining to grab the value of the async clock.
That when you're trying to decode thing, that's going to be in the peripheral. It has its own timer, its own clocks, right?
So they're just in like interrupt, or is it just, or is it like, or this is like, because basically once that time hits, it's reading the value.
Correct.
I was wondering like, how was it like reading the values? Like just like saving that value somewhere?
Yeah.
Like some sort of like a flip flop, or is it just like
just a D flip flop. That's all it is. It just becomes a state holding device. They can choose to do it any way they want. All right. I've thoroughly confused all of you. Maybe I've explained some things. Any other questions about serial interfaces? a great time to ask, because I'll teach you things. All right, you ready for analog? Yes. I want analog, yes. You guys are not as enthusiastic as I am. I don't know why. Analog's pretty good. All right. So, yeah. All right, so we're going to talk about, we're going to be 3 lecture modules. So first we're going to do an overview of analog signals in general. Then we'll talk about specifically ADC, analog digital converter architectures, things that you will have to make decisions on, which architecture to choose in your embedded systems. And then we'll talk about digital to analog converters, where you will be able to make analog values that will, be generated by your STM32. And there's different topologies for this. But first lecture is really trying to give an overview about these theories. Okay, so, I guess philosophically, a microcontroller, the only purpose of a microcontroller, I think, is to interface with the external world, right? You have computers, you can have desktop computers that aren't connected, but that's the type of computing that's not particularly interested, especially for the embedded world. So that's why we spend so much time on UARTs, because that's a digital way to communicate with external or serial peripherals to talk to the external world. And analog is another way to sample the physical world and stimulate this physical world, I guess. So the 2 ways to look at this is we have analog digital converters. So example is a microphone. Although microphones themselves are highly specialized, peripherals are highly specialized, you can think about just some analog signal that you're going to capture. A DAC would be a digital to analog converter where you take some digital bit stream, so some sequential values, and then you're going to send them out and turn them into analog values like a speaker would be. So each year we have microphones are a little bit more rare. Usually it's like sound or clap detection, and then it's relatively easy to make a DAC, or to use the DAC and have it play fairly high quality sound on the STM32. And these are just equivalent, these are commercial equivalents to the equipment you have in labs. So you have function generators, which is equivalent to a DAC, and oscilloscopes were just fancy DACs, or fancy ADCs. So probably the first thing to think about is sampling rate. This is the rate at which things are going to be sampled. So for audio, high quality would be like 44 kilohertz, mid quality 22 kilohertz, and then phones are actually pretty poor, right? There are usually about, at least cell phones and landlines, I suppose, 8 kilohertz. Does anybody know why they only sample at 8 kilohertz?
That it was enough to convey the important parts of human speech while reducing bandwidth so that a lot of people can hear it.
There's a trade-off. Most of human speech is under 8 kilohertz. And very little of it is, while people can make larger, higher sounds, there's not really much information value. So under 8 kilohertz to about, I think they're only like 20 or 200 hertz or so, somewhere in that range is what most audio or voice over the phone is, and that's why it also doesn't sound that great quality sometimes. If you took, I think it's 216 is digital signal processing, is that correct? Yes, maybe. So you should have heard about the Nyquist sampling theorem. Basically says if you want to be able to sample a signal and understand it, you have to sample it twice as fast as the signal itself, and it will enable to recover the signal and understand its frequency components. If you don't, you're going to get aliasing. We'll talk about that. Aliasing is when the digital signal appears to be different, essentially, from the analog value. And it's also important to remember that Nyquist sampling Shannon theorem assumes that there's no noise and there's no clock jitter, which is actually an important assumption that comes into this. So we can think about just sampling a signal here. Sampling a signal is just like, here's a sample, then I measured here, then I measured here, then I measured here. You might say, I set up a timer that will cause an interrupt to occur in which we'll do an ADC sample. So that's one way to ensure that there's a reasonable, consistent time frame for making these measurements. If you just did it in a while one, you may not know, depending on your other things, exactly when you sampled, and then it may change what you think the frequency of the signal is. So take a second. What do you talk amongst yourselves? What do you think the sampling rate is, and what's the frequency of the signal?
Not one.
I didn't realize you that question.
The sample rate should be.
I need you for our five.
So it looks like.
Yep, class size.
Or maybe
One of those dots, so it's 3 zeros. Are you going?
Yeah. Not like really tiny.
Does anybody have the sampling rate? What is it? 2,000 hertz, yep. It's just, there's a period here, so it's 1 over the period. So the time between two things inverted over 1. That will give you the sampling rate. So 2,000 hertz. From what you can tell here, what do you think the period or the frequency of the signal is?
200 hertz.
200 hertz, yep. So how are we going to do that? We're going to say, assume this is the peak. I guess you couldn't really tell, but say this is the peak and this is the peak. What's the time between that? That's going to be your period, and then 1 over that is going to be your frequency. Okay. Pretty easy so far. What about this? This is when you start getting those, can be a little ambiguous. What's the frequency of the signal?
0.
0? What does Nyquist say?
Oh, it's not sampled, no.
So technically, Shannon Nyquist disallows DC as a frequency, but it's just trying to show you the ambiguity that can happen when you're not aware of the sampling. So it's technically possible that I could have this sine wave inside here. In fact, I could have double this sine wave or quadruple or 8 times the sine wave, and still, if I was undersampling too slowly, I wouldn't know what signal I actually have. So you have to be able to choose the right signal, or sorry, know what the right signal is. Same thing here. So here's that same signal that we saw before that was 200 hertz that made the assumption that there wasn't a secret higher signal. So here is another signal that could have generated this. And we were just sampling too slow to understand that, to see that. How about this signal? What do we think this is? How would you even go about figuring out what the signal is? Huh?
You gotta split it into multiple sine waves.
Yeah, this is probably going to be multiple signals on top of each other. From this thing, it would be kind of painful to figure out because there's not that much data, but it just happens to be made of 100 hertz, 400 hertz, and 1600 hertz, and sampled at a rate of 4,000 hertz. Okay. So this comes back to a piece I like to tell people, which is the oscilloscope sampling theorem. It's not my theorem. I just made it up. Basically, oscilloscopes, you're going to set the sampling rate with them, and you should be scheduling at least 5 times faster sampling rate than the actual signal you want. Otherwise, it's going to be really hard to figure out what this thing you're looking at is. In fact, here, you look at a oscilloscope and it says, okay, I got 200 megahertz. That's what it says here. And it says, you can't read it, and I can't read it here. Hopefully I can read it over here. It says 5 gigasamples per second. Here we go. So what does this 200 megahertz mean when you're talking about oscilloscopes? Anybody want to guess?
Is it like the max type of signal they'll allow you to see? Like the most you can zoom in?
Okay, let's go back to this thing. This says 5 gigasamples per second. That's what this stands for. It's 5 gigasamples per second. So how are we meshing these two numbers together? Like, how does one thing have both of these values? Yeah.
Maybe the bandwidth could possibly also be a function of like certain limitations, like frequencies above 200 megahertz won't even get through to whatever's actually doing the measuring.
And which one is that? So you're right, there is a bandwidth limitation. So that's what this top one here is? Okay. So this oscilloscope is rated to take signals up to 200 megahertz. Beyond that, the analog front end, all the circuitry is not able to capture signals going faster than that, even though it can sample at 5 gigasamples per second. It's just saying that Here's its oversampling capability, but its analog bandwidth sampling capability is lower than that. In fact, they purposely make a filter so that you can't get higher order signals, and you don't want to actually get 5 gigasamples or 10 gigasample or 10 gigahertz signals in here. Then you'll be undersampling your signal, and you'll have the same problems we saw in the last slides. And so what you find here is there's also this 4-channel. How is this 4-channel number, which is the number of simultaneous signals that you could be measuring, how does this 4-channel relate to 5 gigasamples and 200 megahertz? Okay, yeah. You got to be loud though.
Each input is sampled at 5 gigasamples per second, and each input individually has a 200 megahertz bandwidth.
It's a good guess. It happens to be incorrect. No worries. What we're saying is this machine can sample any signal, or sorry, its entire sampling capability is 5 gigasamples per second. If you turn on all 4, then you're going to be dividing all 4 channels by 5 gigasamples per second. So imagine there's essentially a mux in here. You have one really fast ADC, and you're going to go past each one of them. So from that, you can see that your oversampling rate is only about 4.25 times the signal, which is close to 5, but it makes sure that a 200 megahertz sample on all those channels is oversampled, or has more oversampled by 4.5 times, making sure that you can actually visually see the signal, and you're not going to be tricked by actually seeing a higher signal on there that you can't understand. So is this helpful when you're looking at instrumentation? Does this make sense? All you wish you never saw analog? Yes.
What the sampling rate is, how it's affected by the channels.
So you're going to divide your sampling rate by the number of channels that you have on, typically. Depends on the piece of hardware. Sometimes it's just the highest frequency it can do. Sometimes they're always going to divide all 4 channels by this, and you can't get any faster than, say, 1.25. But sometimes a nicer oscilloscope will be good to you, in a sense, and allow you to sample at least 1 channel this fast.
Each channel like divider on like
it's just a mux, right? So every 4th signal can go to that channel. All right, so an analog digital converter's job is to take some analog signal and then give you a discrete time representation of that signal. And so you're going to go through, it's going to be quantized in magnitude, right? Because you're going to have different binary values that it can be, and it'll be discretized in time. And so you should think through, when I think about these things, I think about this little ladder here. Well, I'll talk about that in a second, but here's like an analog value, and here is a basic, just for a 3-bit ADC or a 3-bit DAC, the discretization that would occur, right? So you have ambiguity. Here's the voltage signal, and here's the binary value, and you're saying, well, it's somewhere in between here. You have some ambiguity. And the way to think about this is that you have a number of bits. So say in this world is 3 bits, and your ADC or your DAC has a voltage range of, say, in here, 0 to 2 volts, and then you have 2 to the n steps in between. And so now you're going to discretize all those possible analog signals into ADC values, into binary values. So here, right, any value, say, what is this, like 1 to 1.25, any value in here will be turned into 4. You can go through an example. There's different ways to lay this out, so we'll go through different ones, but you can imagine that there's this stair step, and I encourage you not to need the formula. Knowing the we don't give you cheat sheets in the class because you should be able to derive the formulas effectively in your head. All we're saying is, I'm going to go from this is ref low, why is that messed up on this particular slide? That is peculiar. Do I have the right slides? No. That's sad. I made you beautiful new slides. Well, it'll be exciting. Let's go through them. So basically we're saying from this range, from this voltage to this voltage, so this is ref high, this should be lowercase ref low, this should be lowercase ref low. And we're going to say the voltage that you're at times at this range will be divided by this many steps. And we'll say -1, and that's because you can't really actually hit here. 5 volts is basically unattainable, like that 111 in this particular setup is unattainable because there's only one precise voltage value that will exist. So now you can start figuring out what the digital value is, and we're going to use a floor function to whatever it is, we're just essentially going to go to the next lowest whole integer to represent the binary value. So in this particular case, yeah?
What is n again? The 2 to n, the n.
The 2 m's?
2 at the beginning. The 2 to the n. What is the n representing?
Oh, it should be the number of bits. So here we'll go through an example. Here we have 3 bits, and this is a very horrible analog to digital converter or DAC, but 3 bits -1 times 2.8, right? This is, and then where do we get this reference low and reference high from? This is, for this particular ADC, it has to be valid from some range, right? So 0, 0, 0 equals some voltage, 1, 1, 1 equals some voltage. Here it happens to be 0 and 5, so we're just gonna plug those in. So now we get 2.8 over 5, and that comes out to 3.92, and we're going to just go down to the lowest whole integer, right? And that equals 3, so we can see that. There's the problem here is that this is an unattainable value, right? Essentially, no signal is ever going to trigger 111. I mean, sure, if you add absolute 5, but you're kind of biasing that you have a lot of 0 here, but you can get very, very low 111s. And so yep.
So for V reference high, you're just gonna take the highest value, but for V reference low, you're just taking relative to that point?
No, what value, the V reference low, what does 0, 0, 0 equal? What voltage? 0. It doesn't have to. We'll see examples later on where it could be any other voltage. But in this particular example, the lowest bit equals 0. So that would be your low reference, your voltage of your low reference. We have 5 volts here. What happens to equal 111? Right? So that would be your high ref value. And again, this can change. Your ADCs on your STMs is 3.3 volts. And there's actually internal references. I think it's a 2.8 band gap you get, which is more stable than your power supply. And so then your high reference would be 2.8. And so to deal with this fact that this is like nearly impossible to get, most manufacturers will do a half lowest significant bit offset. They'll offset the whole thing over a little bit. And here we can see that the formula has been modified here by adding a half bit. This allows to have, it's not a full bit here, this is a half bit, but you're likely to get some signal here that's actually 111, and you're likely to get 0, 0, 0. And then you can just go through and walk through and modify your equation, and you see that the half bit has actually made this 4 now. That's essentially because this ladder has been moved over by a half a bit to make this stair-step ladder. Yeah.
The reason we do that is because we never actually get to 5 volts, so in order to make the 111 actually usable, you should know it.
Yeah, that's it. And the reality is that this little piece of offset is obfuscated from you most times because it's not so obvious in your ADC that you're going to get that it's a 3 volts. If it was 3 volt or 3-bit ADC, that step is going to be really large, but usually like it's a 12-bit, a 10-bit, a 16-bit. So manufacturers won't even tell you what the offset is because it doesn't matter. So this is just an example of how to go from an analog voltage to a binary value. When we talk about DACs, you can certainly go the other way. You can just invert these formulas to take some binary value, knowing what the low reference 0, 0, 0 voltage equals and what the high reference 111 voltage equals. Then you can go figure out what the analog value you are going to get out is. Then there's the idea of resolution. So you're going to have this ADC. It has some resolution, and we mean the smallest resolution, the smallest analog value that can be discerned. So beware, oftentimes engineers will just quote the number of bits. They'll say, what's the resolution of your ADC? You'll say 12 bits, right? But that's assuming, because you didn't specify what's the resolution of your ADC going from 0 to 5 volts. right? Then they would take the 12 bits, divide it up so that you go and get the actual analog voltage. But resolution really means what's the analog voltage value, the smallest you can get. And there's a couple ways to talk about this. So the way I typically think about it is your reference voltage here, it should be, I'm purposely making it vague because these things can be vague when you see it in the real world. So here's the reference is 0 to 5 volts. This is the high reference because they haven't ever, typically the reference lower reference voltage for ADCs is always 0, it's always ground. It doesn't have to be. If you had a ground that was something else, then you would be Vref high minus Vref low. So it's that voltage range divided by the number of steps you get in here. And that's probably the ideal case. The more precise way to say this is to get the 1 minus 1 in there. But as you see, the delta is small. So if you go for a 12-bit ADC with 3.3 volts, which is relevant to the STM32 case, the difference between these two accounting styles is 0.001, right, millivolts. I'm going to guarantee that's in the noise already of your system. So that's why when you go look at the data sheet sometimes, they are like, they're not going to show you the n minus 1 or 2 to the n minus 1. They're just going to say this is the resolution, this is the step size of our device. Yeah, engineers are not always precise. Yeah, and the error between this is 0.03, sorry, percent. So it's more accurate to use the other expression, but you might have to come back and say, is it actually relevant? And that is because there's quantization error. So in this step size, I can have an analog voltage. So here's an example of a negative rail. It's not 0. Vref low is -4. Vref high is +4. You can have any analog value inside of here, and you don't know. So there's an inherent error in this, and we call it quantization error, and that's going to be 1/2 the lowest significant bit, the smallest value you can measure, your plus or minus 1/2 a volt. Okay? Or 1/2 a LSB. So that's why they're not really caring so much if you're doing the to the n minus 1 in this equation or on the previous slide because it's within your quantization error anyways. All right, so why don't you take a second and figure out for this particular ADC. You should be able to figure out what your quantization error is for a 12-bit ADC with a reference from 0 to 3 volts. Why don't you work with your neighbor, see if you can come up with an answer. What do you think? What is resolution when you're talking about like camera resolution?
3 divided by 2 minus 1. That's the resolution.
Plus or minus.
All you can discard.
So the resolution is the smallest analog value you can measure.
On the same cycle.
2 times 2. Well,
I mean, you told me it's possible, and I think I figured out once.
Smallest. I must have been in my room at like 2:30, but I don't know when I went to bed after that.
I know it's false.
Three. Right? So 3. 3 minus 0. And the big step. Resolution is 0.007.
When this thing comes around, just sign issue valid too.
You ever use calipers before?
Might do some logic with the login.
Whenever this asks that.
Ronnie.
You're dividing by 2 angles.
You drive this.
What's number that it can have? Smallest distance you can
Just say that the
smallest voltage you can measure.
That's how you get it done once.
Voting get
The same cycle.
the 12th bit represents like the least significant bit. Did we just skip that? Like what?
We haven't really written the internal storage yet.
Resolution value.
How are you gonna have time to work on this worksheet?
And I was thinking
Yeah, you just, I was saying you drive this with relationship to this, so you kind of issue
3%, right? Like half of that.
That would be the half of that's quantization.
Quantization error, yeah.
Yep.
kind of like.
What did you get for that?
0.00035. Because my resolution is 0.0007.
Are you gonna go back to this?
Before?
I got that.
Oh.
That's how you did it, because remember, I asked you,
Yes, but I didn't multiply by 2. Why are you multiplying by 2? I don't think
Selection to pass.
your valid bits would be driven.
Just the half part of it.
Oh, like those.
Oh, you did it.
Yeah.
I said plus or minus, I tricked you.
Yeah.
Plus or minus.
Yes.
Talking about the RS entries though, not issue.
Either the absolute value,
I also put it in.
No, that would be driven too. That would be driven.
come back together.
Here, it's like
Here's my answer, and I made a small distinction. How I represented it, because here, value is essentially your lowest significant bit, but it's really plus or minus half of that is probably the more accurate way, because as you take your analog value up, a little bit below your target value, or a little bit higher than your target value, and you're always going back and forth. So one way to represent that is to simply say your plus or minus this amount of voltage. That's the amount of quantization error. And you could just say your LSV, and then you'd have to say that this is, you have to just think that this is your absolute error versus your relative error. Okay. Any questions? Yeah.
Is that error usually just negligible?
So if you have a lot of bits in your system, it's pretty small. And so I think it's probably important as you guys start getting to your project, like your system noise, your power line noise. What influences noise, do you guys think, on your power lines?
Number of wires.
The number of wires. No, number of wires doesn't really matter.
Static voltage.
Static voltage? Nah, not really. Right? You rub your feet in the winter, you're more likely to blow your device up than cause extra noise. I mean, it does cause noise. That's not to say it's wrong, but it's more like what would cause consistent noise that would corrupt things consistently. What do you guys think? What's the source of noise? Yeah?
Induction loops.
Oh, I can't hear you.
Induction loops.
Yeah, induction loops. So, and what is, okay, I'll just tell you. I don't know how to phrase the question. But so in power supplies, right, you oftentimes have loops of wires that are causing magnetic fields, and those can be coupled into other things. Power supplies themselves, especially switching regulators, they switch at a certain frequency, which means there's high frequency content on your bus wires. Another big one is your data lines, I2C, SPI, UART. Those are all making a transition from 1 to 0, 1 to 0. And now that 1 to 0 is pulling current from somewhere, and that's being pulled from your power lines. And now you look at your power line and you will actually see a version of your data on top of your power lines. Now you got your buck converters, your boost converters causing errors. You got your data communications causing errors. What else causes errors? You could have ambient energy, your RF signals are causing errors, especially if you have a wireless transmitter on device. And so what you find is that oftentimes the magnitude of the noise on your power line is larger than the least significant bit of your ADC. And so this rule of thumb for an ADC is the last bit is garbage. It means nothing. Maybe the last 2 bits if your system's not doing so well. And if you need good resolution for those lowest bits, then you have to take extra steps in protecting your analog circuits, protecting the signals that are feeding your analog. And that's why you will see on your STM32s, you actually have separate voltage rails that are protected from their power supply to make sure your analog systems are clean. All right, so signal conditioning. So imagine you have some voltage signal. You have to choose the right range to use. So here we have an example of R plus to R negative. This is reference high, reference low. And if you do this, the problem is the range is too small. And now your ADC is only going to capture this. It's going to think there's square waves coming through. What happened to my analog signal, you might say? Well, you haven't chosen the correct range for your ADCs. So oftentimes on a microcontroller, you'll have an input reference pin where you can choose an analog value from an external source to be V positive. Sometimes it can be VREF negative. Or again, on your STM32, there's different internal sources you can select for these two things. So you got to make sure you're within the right range. The counter example is your range might be too small and your voltage variations might be very small. And so now you know, I don't know exactly what it would be for this system, but say you only have 2 or 3 bits, maybe 4 bits of resolution, and you just not have enough resolution to see this analog signal. So the range is too big. And what you're aiming for is something where the signal, maybe you don't want to go all the way up to the top, just in case it overshoots, but on average it's the full range. This would be the ideal way to recover as much of the information here as possible. Sometimes it's not possible to adjust VREF positive and VREF negative, so that's why we go back to 215 and you add in an amplifier. Just a simple op amp can boost up your signal so that it's within this range. So a lot of the research, a lot of the work my lab does is trying to find a new analog signal out there somewhere and digitize it, because it will help us understand human disease progression or human behavior in some ways. And oftentimes you just need to do a little signal processing, analog signal processing, digital signal processing to get at this signal. So a simple op amp is usually where we start. Any questions? Okay. What was I trying to teach here? Oh. Just a reminder that VREF negative, VREF positive are part of those equations. Those can change. So here you have a 0.3 volts. And here we're just saying that VREF negative 0 is equivalent to 0. 111 is equivalent to 4. So when you put your analog voltage in, you're going to get anywhere in here, because there is some error, you're going to get some binary value. But if you go and change your reference voltages, so 1, say negative, or 1 and 5, and you put in that same 0.3 volts here, or sorry, 3.25 I think is what it was, you're going to get out a different binary value. And that's just because these ranges down here changed. So it's always important to think about, how does this scale match to this scale? And then you know that there's this many steps in between. So that's why I never think about the equations, or never remember the equations. I just think about, how am I going to set up these ratios of each other? Once I understand what this ladder is, then it's just picking out the value and the voltage. And I can go either way. You can go from decimal down to an analog voltage, or vice versa. In your microcontrollers, yes, but something you should think about is that we talked earlier about undersampling a problem, undersampling a signal. So here, you don't necessarily know if it's the blue signal or the red signal that you're sampling. It's an inherent problem. And so what you typically do is you'll go put a filter on the front of it such that you'll remove the red signal, guaranteeing it's not there, so that you're able to undersample your signal. This happens. Sometimes it's inherent to the structure of your ADC, which we'll talk about. Sometimes you explicitly have to put it on your board, but it does mean that you have to think about what is the signal you're trying to capture, such that you're not accidentally getting the red signal. You really need this? Yes, you do. And then here's just the math if you need to go through it. This is basically just 215, maybe 216, just showing you how to calculate out the R's and C's such that you get a cutoff frequency that will reduce the signal that you do not want to get. So that's a brief overview to make sure we're all up to speed on analog signals. Any questions?
Errors at your resolution.
Plus or minus, yeah. Yeah.
Can you go back and explain what this filter does? It just like removes the other frequency, basically?
Yeah, it removes, so say you have put your cutoff frequency such that it's underneath this value, then it'll remove the red one. It will never get into your ADC. So I'll show you an example from a research project. I'm actually going to skip the example that we'll do the worksheet later. But here is a research project I did back at Disney, and it's weird. It's weird. What we wanted to do is make wearable devices, or any device, that would allow a computing system to know what you're holding on to. Right? So how would you figure out what objects you're touching? So you're touching your phone, because the assumption is that we could provide you with better services, right? You would be able to infer, a computing system could infer what you're doing the day. You say, well, when was the last time, where did I leave my phone? Well, you'd have to know when was the last time you touched it. So how can you do that? Well, we came up with this thing called EMSense. Basically, the observation is that all electromechanical devices are emitting EMI, electromagnetic interference. And so this is actually a terrifying event that I went through, and many engineers go through, where you have your favorite consumer electronic device, you're trying to get certified by the FCC, and so you have to take it to be tested. You put it underneath normal workload conditions, and they have an antenna and this anechoic chamber, which does not allow RF reflections, and that they're trying to measure, does it emit signals that break the FCC's guidelines? And why does the FCC have these guidelines? Because you don't want to have all these devices interfering with each other. You don't want to have, I don't know, some Wi-Fi router that takes down a satellite station, which actually has happened. There's an ASUS router somewhere, and it was blinding a military, it's a Earth Science Observation Tower, and they couldn't figure out why. It's because there's something mismanufactured in it, and it was sending out too much 2.1 gigahertz noise. Doesn't matter. But anyways, in this particular case, this is a terrifying event because your little green line went over the blue and the red line, meaning that that's about 6 months more worth of work where you figure that out, and now your boss is super pissed at you. So, but this is happening. As long as you're underneath this signal level, they don't care at all what your modulation type is. That means all these devices are sending out unique signals, or some signals down there. So we made this little device, a little wristband, and all it was an op amp and a Cortex M4 and a Bluetooth module and an ADC that was sampling pretty fast, 2.3 megasamples per second. And so you put it on, and what we notice is that when you touch your phone, there's in your screen here, you got to see some electrical profile. This thing was putting out noise, and now it has some profile. And what we didn't appreciate at first is how unique those profiles are. So here is all the different profiles for all these different devices. So a drill versus an iPad versus all these different things. You grab onto them, and it's sending you a unique signal that's going to couple through your body into our device. And so my students made fancy animations. So basically, you take your RFT, do a little baseband shift. You've taken a background sample, the previous sample before, to figure out what the background EMI is. You basically do some thresholding and send it to a machine learning classifier to detect what object it is. And so this is going to be cut pretty quickly, but a laptop here is connected to this smartwatch, which is going to tell you what it's touching. So here, refrigerator. This is the spark from the stove, toothbrush, scale. All these devices are giving off unique EMI signatures. This is a touch screen underneath here. Drills, sure. Motorcycles. One of the professors had a motorcycle, so we did that one. That door handle was an electric door handle, yes.
How did it know it was like the back door? Is it because it was...
Oh, because we labeled it back door.
Okay.
How big does your database have to be able to characterize all these different things?
You do need to collect the data beforehand and do training on it. It doesn't have to be that big. Now, why did it do ladder? Ladder is not an electromechanical device. Anybody want to guess? Yeah. It's a big antenna. So the students were very excited. Look, we can detect ladders, and I said that's not possible. So they've tried to figure out where is the signal coming from? And what we didn't realize is this was the country radio station in Pittsburgh. It took us a while to figure out because that radio station is not at somewhere below 2.3 megahertz. It's up in there in a much higher frequency, but we were undersampling it, right? It's a higher frequency. We didn't put the filter on their ADC, and now we're undersampling that signal such that now we know that at least you touch a ladder, because we can enable a ladder, but we had this fault signal coming in that we didn't realize, okay? And then just to wrap it up, this is what you would do. It's a confusion matrix. This shows that for device Q or device P, how often is it denoted P? And some of them are good and some of them are bad. And there we go. All right, I'll let you guys go. Thanks.